Okay, and then let me share my screen. Okay, let's start here. Okay, oops. Okay, so here, hold on. Can you see my screen? Hold on, let me move. Can I move this real quick? Let me
Yeah,
move.
sure.
Give me a second. Sorry, give me 1 second. Let me move this to this screen. Okay, decision trees. Okay, I'm so sorry. Share, Rice, MDS, nope. Google Chrome files. Okay, you can see
Yeah, I
my,
can see it now. You can zoom in a bit.
okay, perfect. Okay, so I understand the process. So we start with the algorithm, right? Oh, I remember what we drew is we draw like if we have the plot and then we have it's not good enough for SVM, we have like different regions. We're gonna break them down into boundary decisions, right?
Yes.
So
Yes.
I know the examples are, we don't have to really review that. I think this stuff is pretty straightforward. The estimate of
Hmm.
the value, that's good. So this is the example, right? So if it's less than A, then you go here,
Hmm.
keep breaking it down into the regions of R.
Yes.
Yeah. So I understood all of this. This equation here, though, let me make sure I understand this equation. For classification trees, a class label is assigned to each decision region, non-assigned
Yes.
one, and for oh, because we could do this with classification and regression, right?
Yes.
Of label value is. Can you explain this formula here, Sujay?
This is nothing. This is a choice formula. So what they are saying is, so suppose, let's say we are doing classification. So we divide it into, let's say, a few regions, and each region we assign a label, right?
Yeah.
So now if X belongs to the region with RL, then the corresponding output should be YL.
Yes.
Whereas YL can be a label for classification, YL can be a number for regression.
Okay, so this one is like an indicator function just saying,
Yeah, indicator if it belongs to. This summation is basically only one term. It's
yeah.
just choosing which term.
But if the answer is no, then does this become a zero?
Yes, the one indicator, that's the meaning.
That'll be the zero. Then so region one, this
Yes,
will be zero then,
yes,
right? Okay.
yes. Now you do this repeatedly to make it a tree.
You do this repeatedly to make it a tree. And then when we
Yes,
sum all of them, what are we getting in the, what is y, oh, y hat x. Okay, yeah.
yes,
Getting the predicted value then. Oh, because they'll all have to follow yeses then, right?
yes.
Okay. Okay, perfect. Okay. So this page makes sense. A decision tree which
Yes,
looks at two features to partition the input space into
three
three.
regions.
Okay, got it.
Yes,
So R1, R2, R3. Okay, so that makes sense. I don't have any questions there. This is when it starts getting a little bit difficult. So,
yes. So how do you decide how where to partition, which variable, which feature to look into at any point of time, and those things, and what boundary you put and those things.
okay. It was saying there was a bad way to figure out the splits, right? So the split function chooses the best feature and the best value for the feature.
I don't see what is the bad way of doing it.
I was watching some video about it, Sujay.
Okay.
It was like what are the limitations of splitting on I forgot. I have to watch again. Okay. So
Okay, anyways. Yeah. So the
how
idea here is at any point of time, suppose we have one region and you want to split into more than one region based on a cutoff. Then what we look at is like if after this split, we look at what is the cost for basically in sample and out of sample kind of thing. Sorry, it is in sample training data kind of thing. We are not doing test data yet. So we minimize some kind of cost for all the points where it is on one side and cost for the other side.
Cost being the wrong predictions then?
For prediction, I will assume the cost is non-wrong predictions, but it's not necessary if like if it's a two-way prediction, like +1 -1, then you basically put cost equals 1 if the prediction is wrong and 0 if the prediction is right. If it's a multi-way prediction, it can be more complicated than that.
Okay.
So you can put like if red is classified as green, the cost is this much. If green is classified as red, the cost is this much, and so on.
If it's
And
classified as
those numbers,
blue,
those costs can be
yeah,
like based
right.
on real world cost of like how much is the cost of, let's say, how much is the cost if a patient is wrongly classified as cancer, if it's not cancer, and not cancer is classified as cancer. You can put some numerical, like medical cost to it, maybe.
That makes sense. That makes sense. So that's all this formula is saying then, right? So we have
Yes, that's
the
what the
cost,
formula is saying, that we put this way.
cost of one side plus the cost of the other side. That's all it's saying.
Yes. So T is the threshold here, and Xij is the feature.
T is the threshold here. Yes, T is the threshold. Xij is the feature. Yes, perfect.
Yes.
Perfect.
So it's the jth feature of the ith feature vector.
And it's coming out of our training data set D. Okay.
Yes. For all the points of our training data set.
That makes sense. Perfect. This was a concept I don't really understand is the entropy here. So Jay, this
Okay, so
seems like there was a jump.
this is another way of defining and looking into the classification, how it works and what it measures kind of. So this is like a different, like this is like specifying a specific kind of cost, you would say. This is an example of a cost. The motivation is that when you classify something, there is a way of like measuring. Okay, so I'll put it this way. So there is a way of measuring distance between two classification. So suppose someone has classified ABC in such a manner and someone else classified something else. So there is a mismatch in some of the points, right?
Okay.
It not be that it is matching in some of the points, it is mismatching some. So we want to have a measure between metric between how different these two are. So some kind of similarity measure.
Okay.
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 So entropy is one way of doing that similarity measure. And the way to do that is, suppose you have a discrete random variable, then we define the entropy as expectation of minus log y, log p of y, which is that formula. And by convention, the logarithm is base 2 instead of base 3 or base 10. That's just like.
What is the intuition behind this right here, Sujay?
Oh, so the intuition behind it is, so suppose, so think of it this way. So suppose you know that the population is there, okay, and suppose I pick a point at random, and you know what is the population percentage. So suppose there are the 4 colors, red, blue, green, and purple, and I pick one point at random, one of the balls, and you know how many balls are red and how many green and all that. Okay, now I want you to guess which color it is. Your first guess would probably be whichever is the most common color, right?
Right.
If you have only one guess.
Yeah.
Now, suppose I want you to do those, those questions about, I have thought of a country or a city or a person, and you have to guess by n questions.
Okay. Yes.
Okay. So the intuition, and then you have, what is the minimum number of questions you can guess?
Okay.
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 If you don't know beforehand, and it turns out the optimal strategy is you always try to divide in half.
Because of the decision tree, I guess, because
Because of the decision tree. So suppose like I have thought of a person,
yeah.
you try to ask a question which will roughly divide the total space of people that I could have drawn it from roughly in half. That's like the bisection method.
As in like,
so I will try to I try to eliminate half of the, so like I'm trying to do a binary search on this total set.
yeah, binary search on it.
And yes, binary search kind of thing. And if it takes n questions for me, then basically the space of people is roughly 2 power n.
Okay. Okay.
If 2 power n people are there and I'm trying to do a binary search, then it will roughly take me n questions, right?
N questions, yes, exactly. Yes.
N questions, right? Now, this is assuming all people are equally likely.
Yes. Okay.
So this entropy formula is just adjusting for the fact that all people are not equally likely if you know the probabilities are slightly different.
I was thinking in the question that you were asking, right? Like
Yeah.
maybe the binary first question is less than 50 years or older than 50 years. But then that's
Yes.
maybe a good question because there's less people that are older than 50, right? So
Yes, exactly. So your question, instead of boundary at 50 years, you probably do boundary at 30 or something, 30 or 40,
got it.
whatever is like right in the middle of the population.
Okay. I see what you're
Okay.
saying, but then why does that come to expectation of negative log of P of Y?
It turns out this formula is the correct way of doing that. If you do it, adjusting for the probabilities are different.
Okay. Adjusting for the probabilities are different. Okay. Got it.
Okay. So suppose it takes n different values and each of them probability 1 by n.
Oh, okay. So
Okay.
P of Y is then your probability of Y, like what you were just saying, 1/n then.
Yes. Yes. 1 by n. Kind of thing.
Okay. Okay. Got it. Cool. And eight, so then the final H, what is H then?
Yes. H is the entropy quantity.
Entropy quantity. Okay. And we want to minimize that quantity or something?
We don't want to minimize. We are using this quantity as a metric later on.
We're using this quantity as a metric. Okay, so they've used the example of half and half then here.
Yes.
Okay.
Half and half is like the most difficult to guess, right? So there the entropy is one. Basically, there is a one coin toss information away. It's
So
a 50-50 thing.
50/50.
One coin toss amount of information. You can think of it this way.
One, so
50-50.
does the quantity of one, is that desirable for the entropy? We want it to be one to make sure we split.
Yes. So you can think of it this way. So if a coin is, so if a question is like a half and half, actually, then if I do a coin toss, I'm equally likely to get it correct or wrong, right?
Yeah, yeah, exactly.
But if the probability is something like 80%,
Yeah.
then instead of doing a coin toss, I should choose the one which is 80% rather than choosing the one which is 20%, right?
Sorry.
So suppose, okay, so suppose I have thought of a person A or B,
Okay.
and I'm 80% likely to choose A and 20% likely to choose B.
Yeah.
Instead of randomly doing a coin toss to decide which one you would guess first, you guess A,
Right. 80%. Yeah.
right?
Yep.
80%.
Yeah.
So that means you can do better than coin toss.
You can do better than coin toss. Okay. Yes.
So that's what I'm saying, that if it's 50-50, then it's exactly one coin toss amount of information that is like you don't have.
Got it. Got it. Okay. I see what you're saying. That's
Okay.
that's a little kind of logic, but I understand where you're going with it. Okay.
Yeah.
Okay. What is the goal?
Think of that. Huh?
What is the goal then? Maybe I'm confused because I was thinking in my head the goal
It's
is
not goal. It's a measure of how. So you know standard deviation, right?
standard deviation. Yes.
So every random variable, like if you have a distribution that's a normal or exponential or something, you can calculate the standard deviation there.
Yes.
So
Yeah.
standard deviation kinds of tells you how variable the underlying variable is, like how volatile it is, kind of.
Yes. It
Entropy also does that in a different manner.
got it. Got it. Okay.
Okay, and entropy is particularly good in discrete. Standard deviation is particularly good, more like better for continuous.
Which one's good for continuous? I missed that. Sorry.
Standard deviation is
Standard deviation.
particularly good for continuous variables. Entropy is particularly good for discrete.
Got it. Okay. Okay. Definitely did not know that. That's good. Okay. So we have some joint distribution to find the random samples.
And we define something which is conditional entropy.
Okay. Conditional. So that does say, so we are trying to
To maximize the entropy that remains.
no minimize, Sujay here. Minimize. Our
Sorry,
goal.
minimize, yes. So maximize the entropy that is like already explained.
Okay, got it. Okay. Already explained. Okay. Entropy of Y defined as
Yes.
already explained means the given x of JT. That's what you mean?
So given the value of x,
Exactly.
you already know something about y, right? So how much uncertainty is left? So think of this as variance of x given y kind of thing that we have done earlier.
Okay.
So instead of variance, it's entropy.
Got it.
And then the quantity we have already explained is h of y minus h of y given
That's
x.
why you were saying maximize. Okay, got it.
So you
Okay.
will maximize this quantity. This is the information we have gained.
Yes, and so you want to maximize. Oh, that's what the information gained means then. Okay. Information gained would be the I then, right? I for
That,
information.
yeah, I is the information.
Okay. This makes so much more sense then. Okay, so this is how we train the decision tree. Okay.
Yes. Not yet, but this is one of the metrics that people try to use for the decision tree.
This comes to a matrix.
Metric, like a way of measuring
Metric.
things.
Okay.
Metric.
Okay,
Yes.
okay, this is the metric at least. Okay, got it. Then put the
So, and then you can translate these things from random variables to data where you have empirical, like the ratios instead of actual probabilities.
Okay. As a concrete example, suppose we have 50 apples and 50 oranges. Splitting them by feature shape yields two sets containing 25 apples and oranges each. This has not reduced the uncertainty. Splitting them by color yields set containing 5 oranges and 45 apples.
So, which is very good, right?
That's a good split. Yeah, exactly.
Yes.
Because the sizes of them are too similar.
Yeah, sizes are roughly equal. So if you're trying to blindly classify, you should not do based on size. Apples and oranges are roughly equal. But if you do by color, you will be mostly right. So color is a good feature. Size is not a good feature.
Better split. Okay, so this is our split decision then. Okay.
Yes.
Okay. Gini impurity. He didn't talk about this in class, I don't think. Another way to assess.
These are like different metrics you can use to measure how good we are doing in the classification.
Okay. What is the intuition here then? So we have the sum of the probabilities times.
So for each y, each value of y, we are measuring all the y's which are not. So all the incorrect labeling.
Oh, the incorrect. Okay. Which one is incorrect? The incorrect would be this side.
If
though.
y is k, then everything other than k is incorrect. So all j not equal to k are incorrect, right?
Exactly. Yes. That's why 1 minus. Okay. The intuition. Okay. Perfect. So that's another metric that we can.
Yeah, that's another metric.
This is the one I was saying, the misclassification rate. This is the one
that is ultimately what matters.
Okay. Ultimately, we are interested in the misclassification accuracy. Was suggested we could directly use the misclassification rate. Okay. This is the one that's literally just saying how many did you
got wrong.
Divided.
But we try to do it for the biggest class. Like whatever class we are doing maximum misclassification, we tend to focus on that.
Okay.
So across all classes, whichever class you got the maximum misclassification, so focus on that. Okay. So at any point, that is what one you will try to improve.
That is what the M of Y is what we're trying to improve.
Yes.
Yeah. It's not distinguishable between splits as it may assign the same value to a variety of splits, which are actually.
So that's why this is not directly used.
Good. Okay. And then stopping criteria. It says decision trees can represent arbitrary complex decisions.
So if you don't have a stopping rule, it can go deeper and deeper and deeper.
Yeah.
Ultimately, every class will have only one.
Then
data point.
Yeah, two overfit.
Yes.
Yes. Overfitting. Following 3 heuristics are commonly employed. Limit the depth of the tree by not splitting any further. Do not split further if the proportion of training points. Okay, so this was just to show that we don't want to get overfit. Then do not split further if the gain in information is smaller.
Because it's not.
You got like a predetermined threshold that you.
Yes. Sometimes people also do like if a number of training points is already less than some threshold, like less than 10 points or something, don't split.
Yeah. Okay. Because
that's also possible. Yeah.
Okay. And then the last page here is bagging and random forests.
Okay.
Bagging, I saw it stood for something though, right? Yeah, bootstrap aggregation, right?
Yes.
A common technique used is, I want to understand this because I keep hearing this word.
This is basically majority voting. Instead of asking one expert about the decision, you ask random 10 people and pretend that like whatever majority is voting is more likely to be correct.
What are those 10 people? Those 10 people are your different trees then?
10 different trees. Yes. 10 different trees.
Can you give an example? So maybe the apples and oranges example. So if we had.
Apples and oranges are difficult. Let's do something more complicated. let's say we're trying to classify, let's say cancer versus not cancer,
Okay.
and you have, let's say, maybe some 30 or 40 measurements on each blood sample for the patients.
Okay.
So each blood sample have all the like
Data.
CBC and all those variables. So 30, 40 measurements, right? And now if you try to do a single tree based on those 40 variables, that will be a very complicated tree and getting it will be like even reading it will be complicated.
Okay.
So we can do something like every tree will get to use only 5 or 10 variables, and then we'll create maybe 10 trees. And each tree will try to predict cancer versus non-cancer. And whichever the side gets more votes wins.
Oh, okay.
Okay.
Oh, okay. What is, why do we involve mu and variance here in that?
Oh, this is just giving you an intuition around why averaging can improve compared to individual. So individual trees performance versus the overall majority voting performance can be much better.
Yeah.
And we have like this is analogy to explain to you like if you have n random variables, the average of those have lower variance than any of the individuals.
That makes
If
sense.
all of them has like standard deviation sigma, the average will have standard deviation sigma by root n.
That makes sense.
So by choosing some sufficiently large n, we can reduce it down quite a bit.
Okay. This is not complicated at all. What is boosting?
Yeah. I forgot what is interesting.
Boost, it was like there's different tools I know, like XG Boost and
Yeah. Those are. I forgot which one is boosted. I get confused between these two sometimes. Like
that improves predictive accuracy by training models sequentially. Gradient boosting.
boosting actually combines the methods.
Combines which methods, Sujay?
Must be measurement. So backing is like ask n people and get the majority vote, right?
Okay.
Boosting actually tries to combine those 10 trees into a single tree.
Into a single tree.
Now, how do they do that is the question.
What is the advantage of that? That seems like the opposite of what we want from bagging.
Yes. So there is something called gradient boosting, but that is a very specific thing that people do. There is Hubble laws and stuff like that. So it works this way. So suppose you are doing a regression problem instead of classification, let's say.
Okay.
And typically regression works by minimizing square error loss, right? So now square error basically gives unusually high weightage to the outliers and the points which are far away from your current decision.
Okay.
So this Hubert loss try to kind of reduce their influence by giving less than square. Some instead of doing square, it does something square minus something, let's say. Okay,
Okay.
it doesn't give as much weightage to the
Okay.
extent. So then you Hubert that. So, but boosting also tries to do this by not having all the regressors at the same time. So you create some smaller regression problems by using some subset of regressors, let's say, and then try to combine those into a single regression output
Oh, interesting. Interesting.
while changing the weights of the training data occasionally to make sure that you are like focusing on the problem areas better. So let's say you have 100, you have some 1,000 data points. Some 800 of them you are predicting very well with the ordinary linear regression. Some other 200 is where your problem is, right?
Okay.
Now, when I'm doing a regression tree, I would like my regression tree to focus on that area better than other 800. That because of that other 800, I can use the ordinary linear regression that is good enough.
Yeah.
So
Oh,
boosting is kind of try to artificially increase their influence where the problem lies.
makes sense. Okay. Okay. That makes sense. That makes sense. I don't think you reviewed that in class, and I don't
Okay.
think it's going to be on the test, but it was
Okay.
another word in this context that I kept hearing a lot
Oh,
too.
yeah, makes sense.
And then, yeah, I mean, just for fun talk though, the other
Yes.
one I heard a lot too, Sujay, was like the XG boost. I think
Yes. That is gradient boost.
that's gradient boost. Okay.
Yes.
Okay.
So you use a second order Taylor series and you use regularization like L1 or L2. And there are some strategies on how to do the tree.
Cool. And it looks like in Python, there's just like a package for XG
Yeah,
boost.
yeah, of course, there is a package.
Of course, there's a package. Cool.
Yes.
That was just for my knowledge. It was.
Yeah.
And then lastly, how are we doing on time? Oh, perfect timing. Okay, random forest or an ensemble method. Ensemble method just means many trees, I guess. Is that what that means?
Yes.
Okay. Where the individual models are decision trees trained in a random way. So
Yes.
why is this different than, random forests differ to the bagging procedure in the way the individual trees are trained. Specifically, at each candidate split, the random forests use a random subset of the features. Oh, okay. Oh, okay. So bagging, you're maybe more selective of which features in each tree
Yes.
than random.
Yes.
Oh, because it's
Here you are selecting at random.
okay. So you're just randomly picking subsets for each tree then.
Yes.
And then I'm assuming this is like a voting process then at the end as well too.
Yes. This also has a voting procedure.
Yeah, majority will win
Yes.
the classification. And this can make the individual trees less correlated because it's random assignment of the
Yes.
feature.
Because random assignment. So this is supposed to be the advantage being that this is supposed to be more stable than backing boosting things and ordinary decision trees.
And ordinary decision trees then as well. Yeah,
Because the less correlation thing will supposed to make it more stable.
that makes sense. Okay, buddy, perfect timing. 1 minute left here on this. I think I understand it. Entropy, this is a little, I hope it's this is probably the hard part of it, but I understand.
It's just that you are seeing the definition first time. Like think of this is at a same level as a standard deviation. Like
Yeah,
random variable has a standard deviation that has a definition, right?
yeah, yeah.
There is a formula for that. So this is something similar to that for discrete. There's
Yeah.
a continuous version of also this also, but this is more useful for discrete.
And
And
entropy,
then we are measuring what is the standard deviation of the original and what is standard deviation of the unexplained part. So difference is what is the part we are explaining. So remember this Pythagorean theorem for random variables, variance of y equals expected variance of y given x plus variance of expectation of y given x.
yes, I remember
So
that.
this is the entropy equivalent of that.
Yes, that's what
H of y is the total variability or total entropy uncertainty. H of y given x is the uncertainty that is remaining after what is explained by x.
But
So the difference,
in the variance formula, didn't we add those two together, right?
yeah, so they have written it in a different manner. So H of y equals, just like there we had variance of y equals, this one would be H
Oh,
of y equals.
oh, okay. Oh, we're
Okay.
looking at this then here. Okay.
Yes,
So
yes,
we're adding those two terms together. One term,
yes.
two term.
No, that is just definition of the conditional thing. But the last equation you can rewrite so that H of y is in the left hand side
Plus,
and the other two is basically on the right hand side.
got it. Cool. Okay.
So
Okay,
how much information you have already gained is defined as a difference.
got it. What is what, I'm sorry, then maybe I didn't understand. Which of these terms is considered variance then?
H of y is the variance of y. H of y given x is like the variance of y given x.
So
That is like the variance that is not explained. And I of x comma y is like the variance of expectation of the remaining part, which is the part that is explained. How much if y is explained by x.
got it.
So that is the mutual information.
Cool. Okay, buddy, can we spend a little bit of time on the k-means clustering then real quick?
Yeah, sure.
Then I should be ready for the test. I'm gonna go over this. This one I have not watched any videos or done too much study
Okay.
on. So
Yeah, this is relatively easier stuff than